have done, what I've had with the Moroccan context and later on to the African context. So yes, I do process engineering basically. This is the as I'm hired, but most of activities I have it on the CCUS.
Perfect. And can you tell me a little bit more how you got involved in CCUS?
Yeah, that's very nice question basically. So from the time I finished my PhD, I was still more on the fluidization, the hydrodynamics aspect, mechanical engineering mainly. This was late 2010. And then I got an offer, which was a direct application to what I have learned into a CCUS. That time was basically the chemical looping. So the offer was from SINTEF and then was a joint position with Eindhoven University from 2011, 2 years postdoc. And then I found all the fun in basically chemical looping from that time and then expanded further with SINTEF until 2022, where I moved back to Morocco.
So I didn't know you were working mostly on chemical looping at the early stage. I thought you were always kind of looking at solvent-based technologies.
Right. Basically, I mean, the beauty of working at SINTEF and also the environment was kind of, CCUS was a big topic in Norway in general, but SINTEF was a big driver as well of those ones. And I was exposed to too many technologies with the colleagues there. And then later on as well was involved in a number of EU to national projects and all of them about CCUS and decarbonization. So I will be speaking about the different topics, not only chemical looping, but many other aspects of CCUS.
Perfect. And if you look at the CCUS as a industry, what are the current opportunities in the CCUS area?
But that's from one side is the complexity of things, but from the other side is the beauty is that we are living in a complex industrial world where decarbonization cannot be made only relying only on renewable. So we have several aspects of what we call the hard to abate industry. So we need as well to identify the value chains that can be profitable, linking the decarbonization, renewable energy and CCUS. So I think CCUS now is the hype. Probably is as popular as the hydrogen and water electrolyzer to get the green hydrogen at this stage. And the reason is that because you cannot be decarbonizing mainly based on one specific topic. So I think it will grow substantially high now. And then a lot of science came showing that CCUS will soon take the momentum.
Yeah, I'm sure. And there are career opportunities as well, aren't they?
Absolutely. So those, yeah, absolutely. And in industry-based, basically, is that because first it is knowledge-based. This is one thing. It requires a lot of engineering, from material to process engineering and to also financial and policy engineering. So a lot of careers will be initiated and generated in the CCUS field.
Perfect. And my last question, sorry about my voice, I'm a little bit kind of under the weather today. How people can get started with CCUS research? Like, what are the main trends right now in the kind of knowledge part of the CCUS?
Well, what I'm going to show now, I mean, the diversity of CCUS, from one side, it gives opportunity to many fields of I would say research, technology, whatever, so that they can find their chance to get into CCUS market. And from the other side is again the market is encouraging based. It will be driving creation of job, and I think it can create lots of motivation for fresh graduate to get motivated to pursue basically. The motivation is one thing basically, is that okay, so there is topic which is coming, which is going to solve societal challenges which are linked to the CO2 emissions. Then that's the first thing she's needed. But then again, so you need to start thinking, okay, what topic of CCUS can be closer to my field of study or research. And yeah, probably start from one single project to start building some knowledge about the topic before really digging further into more more career development into it.
That's true. I mean, there is so much aspects of CCUS right now, so I always recommend just start with what's the most interesting one, and then unravel and kind of try to find out what's going on in other areas. Perfect. I think that was very helpful for people who joined the call. We already have the numbers that we are looking at, and I think we can start with the main content for the webinar. So if you could share your screen, if you've got the presentation, and we're going to crack on with your work on the techno-economic assessment of formic acid production by electrochemical route.
Very good, thank you. So I use very little this Google Meet, so I'm just share.
I
found it.
It's very similar to Teams, and people don't have to download anything, so that's the benefit of it.
That's nice. Okay, so I think I'm sharing now. Just let me know if it's not coming.
I think it should come up in a minute.
Yeah.
Let me just check. Are you sharing? I don't see you sharing yet.
Yeah, let me try again. Okay. This one. Yes, and I think it should be coming now.
Yes. Yeah, we can see your screen. Yeah, we can see your presentation. Perfect.
Okay. Let me just put, I have half an hour, right?
Yeah, go ahead. Yeah, I'll keep you to the time.
Very nice, thank you. Yes, so I will use, it's techno-economic prospect of formic acid production, but I will use the opportunity as well to tell a little bit about what we do at the university, where the university is, and the different topics, CCUS that I'm working on, but also the center and who is working on the center. You call me Abdel, they call me here Abdelghafour or Abdelghafour Zaabout. I'm associate professor at Mohammed VI Polytechnic University. So I do process engineering, but most of our activities is for industrial decarbonization. CCUS is big topic, but there are other aspects as well that we look at with the other colleagues that are linking to the renewable energy and green hydrogen batteries and whatever. The university, this is the campus. I think this is an old image, but it's I think a big part of it is existing, or it went beyond what you see here now. It's the campus was built on an area which was made completely green, and it is called the Green City, basically, of Bangrir. It is 70 kilometers from the famous city Marrakesh. So, and you will see there are all the topics of all the hot topics of energy transition, decarbonization, phosphate, so many aspects. You will find them the high topic at the university. I belong to a center which is called ASER, which is Applied Chemistry and Engineering Research, where you will find several of the key topics, the engineering ones, starting from the PV, organic optoelectronics, porous material, membrane. The other part, it's myself, the process engineering and reactor engineering. Let me just show you in the pointer, sorry. So battery and desalination, all the hot topics, you will find them at our center, but also some other people at the university as well are touching. So it's kind of cross-disciplinary research, which is focused on the solving societal challenges linked to the water, food, and energy nexus. The center keeps growing, so it was funded with the previous colleague, Youssef Belmabhout. His big name in porous materials, so Ismail Sadoun, his big name in battery as well. So and others. So I joined later, and then the list is still growing. If I dig a little bit into the wider context, so I think everyone is familiar with these boring types of figures, but they provide the background to why we are doing all of this. This is the CO2 emissions, the yearly CO2 emissions, the current one, and where we will have to go based on the different scenarios that we are drafting. And the scenario, which is I think the most recommended one, is the scenario of 1.5 degrees Celsius global warming to maintain it, and this dictate that we should go to carbon negative emissions starting from 2030 and onward, and the carbon negative part is substantially large as well. So in addition to reducing emission, we will have to go to carbon negative. And this drives a number of of new topics now that they are creating the hype on CCUS, such as direct air capture and BECCS and carbon removal technologies, basically. David, you were asking about the job prospects that can be created by the CCUS. This is a study from Sinter that I think 2019, 2020, so around that. So it was just showing what the industry can be creating in Norway itself. And I'm sure several of the studies has been done in a number of countries, UK, US, and other countries on CCUS, how they can, what job they can be creating and what jobs they can be sustaining, basically, and strengthening. When I come back to Morocco, then it was two main realities were there. The country is now with the large reserve of large potential of renewable energy. This is one, specifically for electrification. And second is that green hydrogen is a main priority as well on the Moroccan side. And then it came as well the roadmap for valorization of bio-based or biogenic waste, so those ones. And then when I came here, and then I'm an expert of CCUS, so starting speaking how CCUS can fit itself into all of this was kind of challenge, specifically from the aspect of changing the mindset, is that renewable energy, green hydrogen can be solving all the emissions. So, but anyway, so I have to explain why CCUS can be really fit into this scenario to consolidate those main priorities rather than really competing. And of course, the statement that I made is that it's knowledge based and it's very diversified industry that can fit very nicely with the priorities that exist on the Moroccan side, and I assume also the African. But then we need to understand this correctly, and we need to do proper screening on what would fit better and in what market scenarios. So if I, again, just repeat what I was saying, so the African context is large renewable energy potential, focus on deployment of an energy transition model based on renewable energy, and then the roadmap for hydrogen and biomass. Those are the key realities that exist, and CCUS needs to find its place, not really enforce it, but really find where it can be applied, and then sell the CCUS as a business opportunity. The key other truth is that the carbon border adjustment mechanism, which is, I think it will be in place from 2026, although the reporting has started. But this carbon adjustment mechanism basically is imposing tax on export to Europe, and I assume it will be as well applied for in the different other areas of the world. So those are creating the incentives for finding what to decarbonize with the CCUS, and how to abate is the one thing, but also to capitalize on the renewable energy potential that Morocco has. Then everything that will be done on CCUS has to be linked to the renewable energy. And of course, you will see here that the green ones and are the renewable energy sources in Africa and Morocco. And then if they are combined with CCUS or CO2 capture, so you can create an infinity of CCUS value chain based, but these value chains has to be and the profitability of those value chains has to be assessed based on the different scenarios, the different market, and from there you decide on whether you take to the geological storage or you take to utilization. CO2 can create provide the carbon source for the methanol and jet fuel, or even the formic acid that I will be speaking about. CO2 can go to the industrial waste. So which is the policy has to drive as well those has to drive the choices to be made and to identify the ones that can be meeting both the policy but also making the expected profitable industry. Renewable energy based driven CCUS value chain. This is one of the things actually that we are focusing on, and the carbon direct removal aspect. The duct is one big activity now, but the duct from the aspect of the ones that they can be used in the electrical energy or renewable energy. These are the one of the focus. And then the BECS as well, biogenic energy CCS. This is as well a second part of the focus in my work. I'm always also in that controversial question: should we go to sequestration or utilization? And when you start road mapping or just basically putting on the table what kind of value chains you can be creating with linking to either sequestration or utilization on the Moroccan side, then you end up with a large number of choices, and those choices, they require proper screening methodology with appropriate key performance indicators to identify the ones that they can be profitable. But anyway, so several factors affect the choice of those ones, and we are still on transition period, even the world is still on transition period in decarbonization in general, and this makes the situation difficult, but it also provides the opportunity to do the screening which is needed to identify the ones that can work for each of the scenarios. I will start with just one slide each on the R&D activities that I'm running here with my team, and then from there I can extend it to the formic acid production study. So the main activities at the current stage are linked to the screening of renewable-based CCUS value chains and identification of the most profitable ones. And then several projects started on this aspect. Basically, is that one of the industries to decarbonize, which is also classified as hard to abate, is the phosphate industry. Drying and calcination, they take a substantial amount of heat, but they also generate CO2 that is part of the calcite, which is forming the rock as well. So the assessment of the different let's say the decarbonization technologies and CCUS basically here because it is hard to abate. So we have looked into implementing the calcium looping for one key reason is that because there is a lot of waste which has calcium here, so it can be directly used in the decarbonization of the industry if it proves to be profitable. And the second is the solvent based. And what we are doing as well through the PhD students, so is that we are looking into combining as well biomass or biogenic waste to bring the carbon negative aspect into those technologies. So study is complete, and then we have some results, but I will not go into it. Biogenic bioenergy with CCS, so we are looking into how to use the wet biogenic waste and decarbonize it to push it to produce hydrogen or even methanol or jet fuel, and then we show how such options can be costing and in what scenarios. Direct air capture, the electrochemical based, a PhD student is working on those ones and attempting to identify the key integration aspects that can make the technology profitable from both aspects. Of course, profitable from the cost aspect, but also the life cycle of it to quantify how much CO2 intensity the technology has. And recently as well, a postdoc started working on implementing adequate CO2 capture and utilization technologies into building environments. So we're assessing such things. Other colleagues as well, they build as well prototype for DAC, passive DAC as well. So that's another work, but it's a hot topic as well on our side. Okay, now I reach the study for which we are here, techno-economic prospect of formic acid production. The study is completed by Bashir El-Gharib, and I'm presenting on his behalf. Pathways for CO2 reduction. So there are, the most known one, the thermochemical. So it's well known how to reduce CO2 into chemicals, methane, methanol, CO, or other. Photochemicals as well is another big topic which is under development, although at lower TRL than the thermochemical ones. And then the one which I will be covering now is the electrochemical one, which is also, we target the first assessment we are making is on formic acid, but other heavier molecules can also be assessed from the techno-economic aspect, but also from the other aspect. Why is formic acid? First, it requires less electrons for fixing the protons into CO2. Although formic acid has much lower energy density compared to other ones, but it has some other features that can prioritize development of a value chain for production of formic acid if it proves to be cost effective, which is the utilization in direct fuel cell for backing up the power within, for example, we'll be checking this in building, but also implementation in microgrids to replace batteries. But the key question now, which comes now, we have CO2 that is coming from, let's say, a capture plant, and a client plan to implement or requesting a specific production capacity of formic acid, and to be powered by renewable energy. And renewable energy with the different mix that exists in a specific region, wind, PV, and plus, of course, you can decide about battery with it. But then the key question now, although some of the studies have looked into the assessment of the cost for the formic acid production, the key question that comes, if now we are changing the geographical location of implementation of formic acid production, what energy mix can be used in that specific location, and what are the key factors that are affecting the cost of production based on that specific energy mix, and how they affect as well the choices, the technological choices on, not only the design choices, not the technological choices, but the design choices on to respond to that specific energy mix and associated intermittency. And then we have looked into this aspect. Basically, is that how the formic acid production will be affected by this renewable energy mix, and how the intermittency is affecting the implementation strategy and cost. The student has looked into the first question came, okay, there are several configurations that one can pick from the literature. Basically, it's not commercial, but there are a lot of studies that are happening now on how to enhance the selectivity, the energy efficiency, and other aspects of formic acid production, and what configuration one would choose for selecting or deciding about the technology to work with. And several factors affect such a choice. First is that, of course, the key one when you are building one. So the energy efficiency is one thing, the selectivity is another thing. but also the impurities that are coming from the different chambers. That's another thing as well, because they decide about the complexity of the plant and how much equipment for the separation and the purification would involve. So the 3-compartment reaction cell that has been selected, so it consists of an anodic compartment where the water splitting takes place, creating protons plus the electrons which are needed for the CO2 reduction. Those electrons that has been created, so they are used in the cathodic compartment where CO2 and water are fed, and the electrons are used to create the formate plus the OH minus. And those ones, the two of them, they go to the central compartment where the protons are further fixed with the formate to create the formic acid. Of course, you have some other byproducts now. That we have the hydrogen, which is produced on the cathode side, but we also have the oxygen, which is produced on the anode side. And those ones, when doing the techno-economic assessments, then they should also take into consideration the separation and purification aspects. The formic acid production plant design, when looking then into the cost, then you will have to take into consideration the different key elements that are needed to provide the purified formic acid product. Plus, we have as well the byproduct that we need to consider, and if they are purified correctly, so they have a market value, oxygen and hydrogen. We assume that we have CO2 that is captured from a specific plant. Okay, let's say we just assign cost into it, and that CO2 is fed to a central electrochemical cell. Then we have the water that is also fed to the cell that I was showing, the 3-compartment cell. And then you have products in the form of formic acid and some other byproducts that we apply proper purification to them to assign a selling price to them as well, that cancel off the part of the, or offset the part of the cost of the production of formic acid. The methodology or the architecture of the model, we decide about a specific production scale or specific installed capacity. This we will show how such thing affects as well, whether it will go for an installed capacity or will go to a constant production scale. They completely affect the design of the electrical system or the energy system that would provide the electricity, and they also affect the final cost, as you will be saying. Then you decide from there. We modeled the electrochemical cell, and in this model, this is where the sizing and the energy consumptions and the products as well are estimated. With the balance of plants, this is what comes as well with the plant, in addition to the key equipment of the plant. And then we have the total power which is needed for running the electrochemical plant for the production of specific capacity. Of course, those ones, they take us to the sizing, design, and configuration, but this we use the system advisor model. And this one basically based on the energy mix which is needed in a specific location and the power which is needed. Then it decides about the sizing of the plant, plus it can estimate the cost of electricity based on that specific energy mix and specific capacity. And all of these are fed into a financial model together with the OPEX and CAPEX. Then we get what we call the levelized cost of the production of formic acid. Then this is just more detail about how the model is working, basically, specifically the model which was implemented in MATLAB Simulink. The mass balance of the different compartments has been implemented at the different level. The anode cathode, the membrane, and then the voltage unit, the mass and the charge balance, basically the electrical balance. And we get as output the different needed information to re-estimate the voltage following a specific current density, plus the other main flow of the product. Once the electrolyzer model is finalized and responding properly, so those information are fed, as I was mentioned, to a system advisor model to design the capacity of the needed electrical energy system with the targeted energy mix between wind, PV, or even I will showcase where we also considered the effect of the grid. Plus, if we would like to increase the storage capacity, the electrical capacity with battery. And then from there, an Excel file is used for the estimation of the levelized cost of formic acid. We started with the model validation, and the key validation that can create a good basis for using for the model for more sizing and estimation of the different key elements of the study was the polarity curve, which is showing the resulting voltage values. The model is the line, while the dots are the experimental prediction. So we see that the model is creating the fit into the expected voltage for the different selected current densities. And then we moved with the further studying now the effect of the other parameters on the cost of the formic acid produced. As I was mentioning now, is that key question that comes, okay, should we go and then we just decide about specific installed capacity? Let's say an example here, 100 megawatt capacity. And then we install within the selected or the targeted energy mix, and then we estimate the cost of the formic acid. Or in another case, we will have to decide about a production capacity, not an installed capacity, and a big difference between the two of them. The key information that can be communicated from this graph is if we start from a different energy mix of electricity, the PV one is the blue, and then we increase the share of wind together with PV, and then we estimate the effect of this mix on the cost. If we have zero storage with battery, the storage we are speaking about battery in hour of storage. So what we see here is that despite the cost of electricity from PV is lower, having a higher mix of wind makes the cost of formic acid production lower for the only single reason, which is the very high capex cost of the formic acid electrochemical cell. And this makes basically that the OPEX, or the cost of electricity, has lower effect, but the capacity factor has the largest effect. So the higher costs require that we can tolerate going to higher costs of electricity, which is involved by the storage, by more battery. You see here, the more we increase the storage capacity, the less difference become between the PV and wind. And this is basically just because of we get to longer capacity factors that we reduce they absorb basically the cost of the capex. If we go to the fixed production capacity, and again you will see the same story now. So what we fix here, we just have gone to a specific energy mix, and then we increase the storage hours of battery, and then we see that higher storage capacity, reduce the cost to a specific level before it starts going up. And the reason is that, again, is just enable a higher capacity factor for the electrolyzer cell. But that's at specific limit, then the storage cost become so it becomes more expensive than really compensating for the getting a higher capacity factor is not anymore paying off. To further visualize now the effect of this capacity factor, so we have gone to a situation where we assume that the backup from the grid can be assumed. So imagine now that we produce using a specific energy mix, but then we can decide on backing up the energy or the electricity supply from the grid when it is needed. And of course, we have done this following as well, replacing part of the grid by the storage. And you will see that the higher is the electricity share that is coming from the grid, the lower becomes the electricity cost, and the lower becomes the cost of formic acid. That's, I mean, we see the effect. But on the other side, what we also assess is that, okay, we would like to utilize CO2 into the formic acid. So it does not make sense to take electricity from the grid unless it is decarbonized. But when we take now the electricity with the emission factors that exist on the grid, then you will see that you are losing against now. I mean, you will be at some stage starting emitting more CO2 than what you are utilizing in the formic acid production. Then, I mean, the first estimation were made from 2030. If now an industrial plant comes and then starts installing in 2030, what would happen? But we also consider what would happen if there are future technological cost development from the different aspects. The aspect of the electrolyzer by itself. So if the required surface area would decrease because with technological advances, then we can reach higher current densities at technologically, basically. But also the improvement that we should expect from the renewable energy system, including the battery. And then obviously we see that, okay, the cost will be dropping with time. 2050, we can reach costs which are close to well, between $500 and $600 per. Sorry, this is ton, not okay, no, this is kilogram. Yes, sorry, this is kilogram. So 60 cents basically of dollar per kilogram. So such thing is feasible in the future, 2050, and this cost is close to what exists in the market currently. The other interesting study as well is to highlight what would be the best location in the world for the production of formic acid, and this is strictly linked to the energy mix and the energy cost, the energy profile, that renewable profile that exists in the different regions. We selected 5 regions that are known with their cheap renewable energy, their high electricity, their high renewable energy potential. But what they have is that they have a different energy mix. If we speak about Saudi Arabia, so we are speaking about very high solar potential with less wind. Morocco in some location, especially the south of Morocco, it has both the wind and also the solar. Norway is well known with wind basically, and then the other one in US. So what we see here is that the cost will be definitely affected by those energy mix. This figure shows what will be the cost if we pick the optimal cost of the electricity with the optimal mix. Then we still see that, okay, Morocco and Norway, because of the high share of wind, so they perform better in terms of cost, while the other one that they are relying more on solar, or with the higher solar energy resources, so it becomes higher because of the capacity factor, basically, that is enabled by a higher share of wind rather than solar. In the second one, we look as well into the changing the energy mix in those regions, basically. And we see again, so that the more we go to the side of wind, the higher or the more profitable or the less costly become the formic acid production. And the less difference become between the different regions, basically, of the world. I'm almost done. So, okay. So if I conclude, basically, what we are given priority here to CCUS value chains with direct interaction with the hydrogen, green hydrogen emissions, plus the value chains that enable negative CO2 emissions, such as VEC and DAC, which seem promising based on the different studies that we have completed. And then we also, a big part of the study, we are doing it in using value chains that enable the recycling of industrial mineral waste. And I finish with this one, the acknowledgement of the of my team and the different collaborators. And thank you for your attention.
Thank you, Abdul. I think that was really great presentation and very well done on the time. So we've got some time left for the questions. And what I'll do, I'll just go through the chat. But if you've got any questions in the meantime, please do send them in the chat as well. So I'll go from the back again. So Nisha is asking, what is the life cycle of the catalyst used? Can you regenerate the catalyst? And is there any regeneration energy associated with that?
That's a very good question from one side, but the other side is that we have not come to really looking into those aspects. So what we looked at now, that's I think one important information that I missed to say in the way we do the design. So we have made this bottom-up approach where we did basically the sizing. We also linked the different amount of material which will be needed for the different components, anode, cathode, membrane, based on experimental data, published experimental data. And those ones, we just consider that they will be having a specific lifetime, and then it will be a replacement time after 80,000 hours, similar to what has been done so far on the electrolysis. But we have not considered that those ones can be recycled and put back into the system.
Okay, perfect. So in terms of the costing, there are a couple of questions around the. Oh, you can see the questions actually. Yeah. So if you look at the cost of carbon that you consider, do you consider it as the external cost to your Technoeconomics? And if so, how it's priced? So looking at whether it's a market value or whether it's a social cost of carbon.
Yes. So we assume the cost of 70 euro, which is a kind of it's in between what is 70 euro per ton of CO2. It's aligned basically with the not with the tax of carbon, but is rather based on expected cost for the capture from specific industrial sites. 70 euro, I think it's in the middle. It's between the 100 euro, which is expected for tax, but it's also aligned well with the prediction of with the cost estimation for specific capture units from the industrial sites.
So it's for industrial sites. It's not.
No, not life. Yes, absolutely. It's industrial sites. Just the capture will not the life cycle cost of CO2. 70 euro is what we have assumed. Okay,
perfect. And do you consider location factor for the capital costs as well?
No, such thing has not been used. That's also a kind of a good, important aspect actually to look at. Is its labors are cheaper on one side than on the other side of the world, the labor. but the capex at the end anyway. So I think you can imagine that the production will of those high-tech elements will start in developed countries, and at the end, I don't think it will be realistic to say that the industry will be moving at early age to Africa or to some other cheap labor regions.
Okay, yeah, makes sense. In terms of kind of going back to capex, did you account for the time value of money in your modeling? So you following net present value analysis, kind of.
That's true.
Yeah,
it's 8% of discount rate has been applied basically on lifetime of 25 years. But what has been assumed as additional capex is the every 80,000 hours of operation with the electrolyzer. Basically, is that a key part of the equipment has been replaced, but including the 8% of interest rate in capex. Yes.
Okay, and I think Antonio raises quite important question. So the technologies that he talked about, they are not at the commercial scale yet. So the TEA is basically prospective TEA. What is the likelihood that your estimates are correct in the future?
You know, it's a very interesting question, and that we always ask ourselves basically is that, okay, what we should assume and what we should not assume. And, you know, all of those cost assessment studies, they're affected by the assumptions. And the need for those standardized assumptions is definitely needed. We tried as much as possible to align with the arena. So what exists most is the arena, so the hydrogen water electrolyzer systems, and then from there, so we assumed, okay, now imagine now that you pick a specific experimental study that has a specific performance with the quantified amount of catalyst that has been used, the different key materials on the different aspects of the electrodes has been used at that stage. And then if you would like to scale it up based on the same assumption that has been made on the lab, what you would basically assume and what you would take. So you upscale basically linearly the cost of, I mean, the amount of material that will be used. That's at least there is no way to miss to make something wrong here. But when you go to the production cost of those specific elements, this is where the assumptions start playing a role. So, and this is where we take the economy of scale into consideration, right?
Yeah, too much.
Yeah.
Yeah. So I think, I don't know whether you've done any assumptions about the class of your estimation. So you've kind of what's the kind of average error that you expect? Would that be plus minus 20%, plus minus 30% at this stage?
You mean on the cost, not on the what's the estimation, right?
Yeah, on the cost estimation.
The cost estimation now, this last graph that I have shown now, basically if there are any technological development, I mean, if we change now the assumptions that we know the world is touching specific current density, for example, per surface area, and then if we get to that current density, how such thing can affect in the cost, you know, because you know we just redesign completely the system based now on higher current density and higher energy efficiency as well. Even if you maximize the current density, you don't have necessarily the same losses that we assume for 2030 for the current one. And from there again, we make another sizing, and we assume as well the expected improvement in cost of renewable energy, and then from there we just recompile everything to get the cost. Is it, I mean, is it 20% more and less? So again, I mean, we tried as much as possible to use the standardized assumptions that are adopted by ARENA. And it's hard to say, okay, how far we are from the realistic one, but we are at least close to the ones that should be predicted within the assumptions made already by ARENA.
Yeah, I think we will need to wait and see. As this technology develops, we would see what the cost actual will be. But looking at the electrolyzer development costs and capital costs, you can draw some parallels between the FA synthesis via electrochemical route, I think,
Absolutely.
because you use similar components, so that should not be much of a difference.
Yeah.
Right, I'm just looking at, if you've got any other questions, feel free to ask.
I see another one here from Antonio.
Yeah, Antonio, yeah. How did you scale the electrochemical production cells? So I think the question is around, did you increase the size of the electrochemical cell, or did you do a modular, more kind of increased number of modules?
It's basically both. No? I mean, imagine now that you have 5 centimeter on both sides cell that has been tested experimentally, and then it had a specific performance. Basically, you get all the performance that is needed: parametric efficiency, energy efficiency, all of those aspects. This is the area, and this is the thickness of the different components. And from there, we scale up this to a specific scale, a maximum specific scale that is realistic, and also in those assumptions from Irena. So there are some specific scale, you cannot go beyond them. So in terms of surface area of one specific electrode. And then from there as well, we just stack them. We assume that we have a stack which can go as well to the maximum that has been also recommended by this Arena. And this is our model that we start with. This is the largest model that we start with. And from there, we do the modular upscaling.
Yeah. Okay. So you've got a maximum value for each module, and then you upscale numbers of modules where possible.
Yes.
To get the desired. Yeah. I think that's how we would see this technology will develop over time as well. I think very good questions. From my perspective, obviously you sent on the formic acid, and just wanted to understand why formic acid in the first place. I'm asking because I did a presentation earlier this week on petrochemicals, and potentially there is an opportunity for methanol synthesis as well. Is there market for formic acid, or is methanol a bigger market comparing to this?
No, definitely methanol has much larger market than formic acid at this stage. The main driving force for the formic acid is, again, so it requires 2 electrons to fix the proton, so it's the easiest to get and the less energy intensive. This is one. And second, it was an expectation that the formic acid fuel cell can be used basically in a number of places, specifically in microgrids, areas where we can play the role of an energy backup to those instead of batteries, basically. So it's like an energy storage medium, so we can store the renewable energy at cheaper energy cost. Plus, you can reuse it for the backup of the energy. And then we are looking as well into now how to implement in building now is that also the involved losses in terms of production, but also the utilization can be used for the recover that heat and then pump into the heating the inbuilt environment. So that's the main driving force, but the market is still small for formic acid. Okay,
good. Because at the end of the day, you would need to replace any fossil fuel derivatives with alternatives at some point.
Yeah.
We cannot simply go renewables because we use much more than renewables right now.
Absolutely.
I think Europe is asking, what is the current efficiency, and on what basis are you considering improvement in efficiency over the years?
The answer is yes. No, I don't think that there are any differences between the electrochemical reduction cells and the electrolyzer by themselves, the water electrolyzer. So they will follow the same path, and whatever learning that has happened so far on the green hydrogen production can be directly applied to the other one. So the improvement in current density can be done in several aspects, basically on the material engineering. Plus as well, so we were earlier as well looking into how to evacuate the heat from those losses in way that you can push to the maximum temperature for maximum current densities without killing the electrodes. So the improvement will happen, I assume, But again, so we can readjust anytime the model prediction to to reaccount for any changes.
Yeah, once you have the model, it's fairly straightforward to update that, and then it will give you a little bit better accuracy predictions.
Absolutely.
How did you validate your models? I'm just curious. Have you done experiments?
Yes, well, basically we're buying a number of, we are buying several configuration of basically electrolyzer, but you can do whatever you want with them. But they target having enough flexibility on how many chambers or compartments you can be creating. So in a way that we can be playing with those. So the validation, but the validation that has happened now with existing results from the literature. So we showed a graph that is showing at least the current density against voltage and be predicted correctly.
Excuse me. That's really good. I mean, at the end of the day, you need to validate your models because otherwise you need that credibility to make sure that the prediction is correct. I think, do we have any final questions? We've got 3 minutes left, but if maybe you have, Abdul, any questions to the audience or something you want to encourage them to do as a result of your presentation?
No, basically it's this, we know that the improvement will happen based on those experiments, more catalyzed development, more electrode development, whatever. So if there are anyone from the audience who is working on the field and would like to, and if they have a different configuration than the one that we have simulated, we can implement such a configuration as well with the data of the experiment that they have got, and then bring the cost of that specific configuration, plus probably also direction on where to improve, where to do more of the R&D.
Yes, that's something I might need to talk to you about at some point. Which is good. Okay, final question from Yurvay, and it's fine you asking questions. That's why we do that Q&A session. We want to encourage that discussion. So for the carbon tax, you consider it for energy, but is there any reason you haven't considered a carbon credit for the carbon that you saved?
Well, all of this is linked to a policy. So one would argue that we are, depending on how we are going to use that formic acid, if the CO2 is emitted back to the atmosphere, it's even at some stage would not be considered as a carbon sinking pathway. Using the CO2 from biogenic source can play a role, but again, depending on whether what you do with that formic acid. The nice thing about those formic acid fuel cell is that you get back your concentrated CO2 after you do the conversion. You extract the energy which is in it. So we can probably set up a working and a business model on recovering that CO2 after if it is used, of course, in the fuel cell, to recollect it and send it for storage or permanent sequestration, and then you can claim either tax reduction, or you can claim as well a carbon credit, or if CO2 from a biogenic source is used.
Perfect. Yeah, it's all linked to the policies and where that specific unit is located and whether there are any carbon credits available, actually, because for many cases they are not yet.
Absolutely.
Okay, we've hit 11 a.m. If you've got any follow-up questions, please send them to me or to Abdel. So the session will be available on LinkedIn and then later on YouTube as well. If you've got any follow-up questions, let us know. I think very well done for everyone who joined today. This is the 5th webinar in the series that we've done already, and that kind of ends the series of our webinars. So what we're doing right now is we're actually looking into doing that on a more regular basis in the next year of the course action, and we'll be in touch with the call for presenters somewhere in October. And then we're going to plan for the next 6 to 12 months with those webinars, because from the feedback I've got and we've got as a kind of presenters, they seem to be quite positive thing for the community, and hopefully it gives you an idea of what's going on within the research community, but also gives you opportunity to showcase your research and build your expert profile. So I want also to use this opportunity to kind of invite people to the Net Zero Feasibility, which is on the 1st and the 2nd October. That will be, again, similar kind of virtual seminar or CCS. We've got 8 very interesting speakers across different areas of CCUS, both policy, social, techno-economic, lifecycle assessments. So I'm pretty sure it will be interesting. So if you want to join the session, do let me know. I'll send you a link, but I'm sure Anna or Kenan will disseminate that as well. Thank you very much to Abdul for today's session. It's been very informative. It shows that kind of doing electrochemistry and electrochemical reduction of CO2 could benefit from the technology point of view, because you basically decarbonize this process, but also from the business perspective, the cost will not be that prohibitive, right? It will be pretty similar from what I gathered from the presentation. So very well done. Thank you for joining, everyone, and I'll see you soon.
Thank you very much. Thanks to everyone.
Thank you.
So